Let's pray and we will get started. Father, help us with Monday afternoon energy levels to just be ready to teach and to learn. Help me to be clear and accurate and concise. And Father, the things that we're learning, would they be for our good and or to be fully prepared for whatever classes students may have in the future that would require these skills or this knowledge. We pray this in Jesus' name. Amen. All right, so we're back to PV equals nRT, ideal gas law, and we're going to work on today is starting to kind of manipulate it and do different things with like density and molar mass and stuff like that. So one of the things that the book wants you to just be really cognizant of is the concept of STP. That marker is not working very well at all. So STP, standard temperature and pressure, right? So standard temperature is going to be 273.15 degrees Kelvin. Right, so 0 degrees centigrade. Pressure standard is going to be 1 atmosphere, right? And so, and we'll see this coming in a minute. Just the ability to hopefully know quickly, like something like 1 atmosphere is 760 torr or something like that, to be able to run through them. So we're not having to flip-flop our constants and things. Is just helpful. Some other aspects of STP is, and you may remember this from last semester, 1 mole of an ideal gas occupies what volume? Do you remember?
It's 1 point something liters.
22.4 liters, right?
Yeah.
Okay.
Far off it.
Yeah, it's all good. In fact, I think they have one of these. Okay, so 22.4 liters doesn't go as far as you might think it does.
It has 22.4.
That's what it. Yeah, I trust it. It's fun to spin anyway. So my kids would have a ball with this. I'm just a big kid myself. So that's how much 1 mole of any gas, by the way, any gas, regardless of its molar mass, regardless of whether it's like an inert gas, like helium, or whether it's diatomic, like oxygen, or whether it's a large molecule, like if you had 1 gas of ethane or something, or ethene or ethine, that's the volume that it's going to occupy under STP. Okay, let's roll on. So you don't care about any of that. Let's do some math. Density and molar mass is kind of where we're going to start off. Man, these markers just not that good. Let's try this one. Blowing through these things. Density and molar mass. Okay. So the ideal gas law described previously in the chapter relates to properties of pressure and volume and temperature and the molar amount in. This law is universal, right? We know that PV equals nRT. We know these parts: pressure, volume, moles, ideal gas constant, and temperature. Rearranging the ideal gas equation to solve for V, skipping a step. We also know that for density, right, you get this equals mass over volume, right? So we got volume in both parts, so we can arrange this to solve for volume, and we can arrange this to solve for volume, and we can use density in here, which is kind of cool. So if I rearrange this to solve for volume, then I get V equals nRT over P. If I rearrange this to solve for volume, then I get M over D, volume equals M over D, right? So I could substitute that. I could do mass over density and do tricks. So that's what we're going to look at doing here. So rearranging the ideal gas equation to isolate V and substituting into the density equation yields this, so when I put these two things together, I get density equals MP over nRT. Right? Is that right? Okay. And it says then the ratio of mass to moles is the definition of molar mass, right? So it's having us take this a step farther. Molar mass, and I'm not very good at drawing these things like this, but we'll try it, equals mass over the number of moles, right? That's easy enough. The density equation can then be written in this way. Because we got mass over moles, right? Mass over moles. So I can simply take that component out, put in molar mass. So density equals molar mass times pressure divided by ideal gas constant times temperature. So far so good? Okay. So now we come up with this question. What is the density of molecular nitrogen at STP? So find density of N2 at STP. Okay, so simple lead off here. So we're looking for density. Density equals molar mass times pressure over RT. So we'll go ahead and we'll plug in molar mass of nitrogen. It's diatomic nitrogen. Do you need one?
No, I think
Okay, good.
it's 14.007, so times 2.
Times 2, so
28.0.
28.01, I believe.
Yeah.
Okay, grams per mole, right? Times it's at STP, so our pressure is 1 atmosphere. And R, we're going to go 0.0821?
8206.
Doing 8206, not 821. Now we just round it. 821.
Okay.
Oh, and I needed the 0 that I didn't have. 0.0821. And that's liters, atmospheres per mole per Kelvin. Right? Okay. And this times standard temperature, which is 273.15 degrees Kelvin. Right? Okay, so when I divide 28.01 by 0.082 and also by 273.15, what do you get? Got an answer?
1.25.
Yeah, 1.25 grams per liter. Okay. Good. Okay, let's do a follow-up problem with that. Okay. Find the density of molecular hydrogen at 17 degrees Celsius and 760 torr. Okay. So my formula of this again is density equals molar mass times pressure over RT, right? Okay, so when I go ahead and do this, my molar mass of hydrogen is 2 times pressure, 760 torr, and I'm probably going to want to keep my same ideal gas constant, so I'm going to want to go times 1 atmosphere over 760 torr, right, which I know is 1. Okay, and then I'm going to put this over 0.0821, and that's, I always forget my units for this, it's liters, atmospheres per mole, Kelvin, right? Times my temperature is 17 plus 273.15, puts me at 290.15 degrees Kelvin, okay? So that's my formula. I have a song in my head. I literally couldn't think there for a minute because I had a song going. So what'd you get?
1084.
0.0847 grams per liter. That's it. Very good. Okay. When the identity of a gas is unknown, the measurements of the mass, the pressure, the volume, and the temperature of a sample can be used to calculate the molar mass of the gas, a useful property for identification purposes. Combining the ideal gas equation and the definition of molar mass yields these equations. So, using PV equals nRT, and knowing that molar mass equals moles, or mass per mole, then I can solve this, and I was doing this earlier. Let's walk through it just to know that the math works. Depending on the problem that you run into, like, hey, you may actually have to do this the long way around, right? So the thing they have in common is the moles, right? So we're going to go PV over RT equals N, right? Okay. And on the other side, we're going to have N equals, what, moles over molar mass, is that right?
Yeah.
Okay.
It's mass over molar.
Yeah, sort of.
Yeah.
Okay. Did I say it wrong? I might have. There's no telling me. Okay. So that tells me that I can then have PV over RT equals this, right? But it's wanting me to solve it for this, right? So to do that, this is where my head gets, you know, I'm not a math guy, so my head gets flipped upside down sometimes, but
It would be MPV divided by RT.
say it again.
It's going to be the molar mass.
Oh, to just, yeah. I had found a, well, I guess not simpler, but maybe more straightforward method earlier. But I can keep working this out, right? And I can go, here we go, long way to get there. I was inverting things and stuff. You don't need, I've got all these thoughts, all these backstories about me and math. We're not really close friends, we're acquaintances, frenemies really. Anyway, so essentially this is the formula that we need, right? Is that molar mass equals nRT over PV, okay? We did all that to get to that. Okay. So now it wants us to solve some equations doing this, or some problems doing this. So I'm going to erase. Okay. Cyclopentane, a gas once used with oxygen as a general anesthetic, is composed of 85.7% carbon, and 14.3% hydrogen. Find the empirical, oh, I'm sorry, find the empirical formula. And if 1.56 grams of cyclopentane occupies a volume of 1 liter at 0.984 atmospheres and 50 degrees centigrade, what is the molecular formula? Okay, so let's just back up and talk about how to do this. I'm sure you remember, but my percent carbon, my percent hydrogen, they're going to add up to 100%. How do we go about solving this?
I feel like if you find the molecular formula first,
Mhm.
it's easier to find the empirical formula.
Well, all right. Carbon. So or let's do it this way. 0.857 times, it's my formula for my molecular mass of carbon, 12.01,
Yeah.
equals X.
I think it's 83.7. So it's 0.837.
Oh,
Yeah,
there you go. Okay. And hydrogen is 0.143 times 1, right?
Mm-hmm.
Okay, so what is 12 times 0.837? Let's solve for that first.
.05.
10.05, okay, and 0.143 times 1 is
0.143.
0.143. Okay. I need to come up with some whole numbers, right? So one thing that may be useful is to divide it by see if they like to get it. I'm going without it or not. We're going a little different method about it. Let's take a look at theirs. So they say first determine the empirical formula of the gas. Assume 100 grams and convert the percentage of each element into grams. Okay, so I would have 83.7 grams of carbon, and I would have 14.3 grams of hydrogen, right? And determine the number of moles of carbon and determine the number of hydrogen in the 100-gram sample. So I would divide my 83.7 divided by 12.01, right? And I divide this by 1. So 83.7 divided by, oh, yeah, they did different than I did. What am I going to get here?
6.97.
6.97, which means it's going to be 7, and this is going to be 14, right? So it means I should have about a 7 to 14, right? So C7, H14. And did they like that? Is that what they got? Okay, but we're going for empirical, right? So I can simplify this, divide everything by 7, so I'm going to get C, H, 2, right? Okay, very good. Okay, so now I need a marker that's going to work. 2 of those were brand new. Did not work. All right, so moving on to the next part of this. We know the empirical formula is CH2. The empirical mass is 14.03 grams. Next, use the provided values for mass, pressure, temperature, and volume to compute the molar mass of the gas. Okay, so it's all right. So I know that my molar mass equals mass times ideal gas constant times temperature divided by pressure times volume, right? So now I can just start plugging things in, right? Where are you get here? 1.86 or 56 grams, though. Oh, because, okay. I forgot that it gave me that. Okay, so it's wanting me to now to use 1.56 grams. Yeah, that's provided in the second half of this problem. 1.56 grams. Let's just plug it in. Times my ideal gas constant 0.0821, right? And that's what, moles, liters per.
Liter ATM per mole.
Oh, liters, atmospheres per mole
Kelvin.
per Kelvin. Okay, thank you, sir. All right. I take that and I multiply that by my temperature, which they're giving me of 50 degrees centigrade. Is that right?
Mm-hmm.
Okay, so 50 plus 273.15 is
323.5.
123.15 degrees Kelvin. And I'm going to divide that by my pressure, and my pressure is 0.984 atmospheres. And I'm going to multiply that by my volume, which they're giving me of 1 liter. And so when I do all of that, I'm going to have a molar mass.
Hopefully.
Oh.
I got 43.38.
43 point, what'd you get?
38.
Should be 42, they say. Let me check that.
Yeah, it's 43.3833955975.
Yeah, but they're just saying it should be flat out 42.0. I'm just going to run my real quick. 1.56 times 42.06. Okay, so 42.0. All right. That's my molecular mass. Molecular mass is 42.0. Empirical mass is 14, right? So 12 plus 2 is 14. 14 grams per mole. Grams per mole. So really my question is, how many of this multiple of CH2 does it take to get to that, right? So I can divide 42 by 14. And when I do that, what do I get?
3.
Equals 3, right? So 3 times CH2 is going to give me C3H6. And that's the correct answer. Okay, we're going to do 2 things. I'm going to write this, or 3 things. I'm going to write this problem up. I'm going to go find more markers. I'm going to use the restroom. And you're going to solve the problem. We'll come back. All right. Too much sweet tea at lunch. Acetylene, a fuel used for welding torches, is composed of 92.3% carbon and 7.7% hydrogen, right? So find the empirical formula. And if I'll put this part over here. It'll just help to break these down into 2 parts. I think. Okay. Probably wanted that up there, didn't you? Molar mass times, what is it? Mass times RT over PV, or equals?
It's molar mass equals nRT over PV.
Yeah, thank you, sir. Molar mass equals nRT over PV. Okay, so now on this one it says given 1.10 grams of acetylene, occupies a volume of 1 liter at 1.15 atmospheres and 59.5 degrees centigrade. Find the molecular formula. Okay, solve for it. I'll be back. What do you got for me?
Okay, I got this one I got CH.
How'd you do it? 92.3 divided by 12?
Yeah.
Right, and what did that come to?
7.7
7.7. And H?
is 7.7 divided by 1 is 7.7.
7.7. Okay.
Got CH.
So you get a CH. Okay, good. Now we come over here. And we're solving for molar mass, right? Because we're going to divide molar mass by empirical mass. So I take my mass, my 1.10 grams, multiply it by 0.0821, blah, 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 times my temperature, which is
332.65.
332.65, right? Now I divide that by my pressure, which is 1.15 atmospheres, times my volume, right? And when I solve all that, I get
26.12.
26.12. Now I take my 26.12 and I divide that by my empirical, which was CH, so that's 12 plus 1 equals 13.1, and that gets me a 2, or a times 2 ratio, right? So my actual formula is going to be
C2H2.
C2H2, which I trust is the right answer. Yeah, there we go. Okay, we did it. Well, let's erase and do the next thing. So here we go. Determining the molar mass of a volatile liquid. The approximate molar mass of a volatile liquid can be determined by these steps. Number 1, heating the sample of the liquid in a flask with a tiny hole at the top, which converts the liquid into gas that may escape through the hole. Then removing the flask from the heat at the instant when the last bit of liquid becomes gas, at which time the flask will be filled with only gaseous sample at ambient pressure. Sealing the flask and permitting the gaseous sample to condense to liquid, and then weighing the flask to determine the sample's new mass. Okay. Using this procedure, did that make sense to you? Let's see. So you heat a sample of liquid in a flask with a tiny hole at the top, which converts the liquid into gas which may escape the hole. So we're not collecting this, we're just heating and letting it go. Okay. Then removing the flask from the heat at the instant, the last tiny bit of liquid becomes gas, at which time the flask will be filled with only gaseous sample at ambient pressure. So whatever, pressure is outside because it's been able to escape, so it's, it's not, so that's good. Okay, then sealing the flask and permitting the gaseous sample to condense to liquid. Then weighing the flask to determine the sample's mass. I assume that we've already weighed the mass of the sample, or the flask. Okay, got it.
I understand that.
Using this procedure, a sample of chloroform, and we know the volume of the flask, right, ideally, so okay. So we're going to know volume, we're going to know pressure, we're going to know temperature, right? Now we're going to solve for mass, and we should be able to come up with something, right? Some molar mass or things like that. Using the procedure, a sample of chloroform gas weighing 0.494 grams is collected in a flask with a volume of 129 cubic centimeters. At 99.6 degrees centigrade, when the atmospheric pressure is 700, what am I doing? Let's try that again. 742.1 millimeters of mercury. What is the approximate molar mass of chloroform? So we're trying to find this, right? Molar mass of chloroform. So we did some problems with molar mass a minute ago, and we said molar mass equals mass times the pressure volume on top.
No,
RT on top.
Yeah, RT.
RT over
PV.
pressure and volume. Okay, good. This shouldn't be too hard. So I'm going to take my mass, which is my 0.494 grams, and I'm going to multiply it by 0.0821, right?
Yeah.
And I am then, because I'm tired of all those, I'm going to multiply that by my temperature, which is 99.6 plus 273.15. Which gives you, oh, just erased.
372.75.
372.75.
Yeah.
Okay, good. And now I need to divide all of that by my pressure and my volume. My pressure is going to be 742.1 millimeters of mercury, which I'm going to need to convert, right? And so what am I going to convert that into? Do you have that sheet? I got a sheet. You need one?
I got it.
You got it. Okay. So I want to get from millimeters of mercury into atmospheres.
You can divide by 760. Multiply by 1, and you get on 4. And then divide by 760.
Good. So I can put this over 760, and that's millimeters per atmosphere, right? And now I can multiply that by 372.75, right? To keep this simple, I can probably just put my 760 up here.
It's not 372.75.
What is it?
It's the volume, it's 129 centimeters.
How did I get it? Oh,
You put the
I
temperature.
looked at the wrong thing. Okay, great, awesome. Okay, I'm doing 0.129 liters, right? Because I'm going to go ahead and take that for granted. Now this 760, I don't like doing math within my math, so I can probably just take that and put it up here, right? 760. Atmospheres over per millimeter.
It's 1 torr per atmosphere.
Yeah. Okay. So let's go ahead and solve. What'd you get? Okay.
Got 1.997. I think there's something wrong.
Something's wrong. Run those numbers again.
Okay.
What you got?
120?
120. Good. Very good. Or I guess it's grams per mole, isn't it?
Yeah.
Okay. All right. Well, let's do one more of these. A sample of phosphorus that weighs 3.243 times 10 to the negative second grams exerts a pressure of 31.89 kilopascals in a 56.0 milliliter bulb at 550 degrees centigrade. Okay, so they want to mess with us a little bit here.
Yeah.
And what are we trying to do? We're trying to find molar mass, is that right?
Mhm.
What's the molar mass and the molecular formula of the phosphorus vapor? Okay, so we just do that, we find the molecular mass and divide by, or by the mass of phosphorus. So, okay, so molar mass equals my mass, which is 3.243 times 10 to the negative second grams, times 0.0821 times my temperature, which is 550 plus, yeah, you do that, I'm not doing that.
823.15.
823.15 degrees Kelvin, okay? Divided by P, what is my pressure?
It's
My pressure here is 31.89 kilopascals, so I got to get from kilopascals into atmospheres, right? So, 1 atmosphere, where's my...
One atmosphere is 101,325 Pascal.
Okay. So I probably want to begin by converting this kilopascals to pascals, right? Times 1,000 Pascal per kilopascals. And then I want to, so you got how many pascals per atmosphere? I want to divide that by what do we have here? 101,325 pascals per atmosphere, right? And then I want to multiply all of this times my volume, which is 0.056 liters, right? I got to be sure to convert to atmospheres, convert to liters, so that my ideal gas constant works out. If I don't do that, that's not the right constant for what we're doing. So we let that dictate what we're doing. So one thing we can do real easily is we can put this up top. I just like to do that. I think it makes life a little easier. So 101,325, that's going to be atmospheres per Pascal, which then will allow all that to cancel out, right? So I'm going to go ahead and I'm going to eliminate this. That keeps me with just simple straight line multiplication and division. So plug that in and we get 3.243. I'm going to, these calculators are not that good. 0.03243, right? That's what that's equivalent to, times 0.0821 times 823.15 times 101,325 divided by 31.89 divided by 1,000 divided by 0.056. look like my answer? That's the question. Yeah, it does. What'd you get?
I got 124.7.
That's right. Good. So we get 124 what is it, grams per mole?
Yeah.
Okay. Is that right? 125 or 124? 124. 125 grams or 4 grams per mole. Now, if I divide that by the mass of phosphorus, what do I get? That's phosphorus. 1 divided by how much?
It's 30.974, so 31.
I get 4 here. So let's see what it says. Yeah, P4. So P4 is my molecular formula. Okay. Well, good. Let's look at some other stuff. Partial pressures. Unless they chemically react with each other, which does sometimes happen, the individual gases in a mixture of gases do not affect each other's pressure. Each individual gas in a mixture exerts the same pressure that it would exert if it were present alone in the container. The pressure exerted by each individual gas in a mixture is called its partial pressure. This observation is summarized by Dalton's law of partial pressure. The total pressure of a mixture of ideal gases is equal to the sum of the partial pressures of all the component gases. So, saying P total is equal to pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3, etc., etc., etc. Another way of saying it is that P total is equal to the sum. Come on. Why can't I do a sigma? Is equal to the sum of all the pressures. Okay. Okay. In the equation, P total is the total pressure of the mixture of gases. P1 is the partial pressure of gas 1, P2 is the partial gas, etc., etc. These things are self-evident. Okay. Partial pressure of gas A is related to the total pressure of the... What? Partial pressure of the first gas is related to the total pressure of the gas mixture by its mole fraction, a unit of concentration defined as the number of moles of a component of solution divided by the total number of moles of all components. Wow, they're just throwing that at us like wild. Okay. Partial pressure of gas A equals its mole fraction. That's what that is, mole fraction. Times the total pressure. Where this is the number of moles of A divided by the number of moles of the total. When we remember that this has nothing to do with their mass, this has everything, everything to do with just every type of gas, no matter what, at standard temperature pressure, 1 mole equals 22.4. They're all going to exert in the same way. Then, because I'm not worried about mass, I'm only worried about moles here, You know, if I have half a mole, well, that mole is going to account for half of the pressure of the whole thing, right? So there's just different ways of thinking about the same idea. All right. Let's do some work with it. So it says we have a 10.0 liter vessel, and it contains the following. 2.50 times 10 to the negative third moles of H2. And it also has 1.00 times 10 to the negative third moles of helium. And it has 3.00 times 10 to the negative fourth moles of neon. And all of this is happening at 35 degrees centigrade. Okay, so the first part of this is what are the partial pressures of each of the gases, right? So what I need to know is how, as a percentage, what do I have of each one, right? So I can use this to help me solve for that, right? So how many moles do I have total? That's the first thing that we need to ask ourselves, right? So I'm going to do this longhand. I see right? Okay. So if I go ahead and I add all this up, I get 0.0038. See right? It's the number of moles. Okay. So to find out any one, I just need to divide the amount it represents by the whole thing. All right, so what is it asking me for to begin with here? I'm trying to solve for what are the partial pressures of each gas. You give me the pressure of the whole gas.
Yeah, that's what I was about to ask. You need the
A 10 liter vessel contains X moles, X moles, X moles at 35 degrees centigrade.
I think you need to do like the nRT and all those to get the pressure, and then do the summation, because he gave you the volume and the temperature.
Yeah, let me see here. So they want 100 moles, that one, times let's see. So we got PV equals nRT, right? So we want to solve for the pressure total. Right? So P equals nRT over V. Right? So this was useful because I know my total number of moles right now, right? So I'm going to go 0.0038 moles times 0.0821 times my temperature, which is 273.15 plus 35, which is
308.15.
308.15. Okay? And now I'm going to take that and divide it by volume, which is 10 liters, right?
Yeah.
Okay, and so when we do that, what do we get? Yeah. So it comes out this way, or it can be it can be 9.61 times 10 to the negative third atmospheres, right? That's the total pressure, right? So I don't know, I guess my inclination is to work this backwards of how the book wants you to solve it. I like to go this route and then divide that by this, and that'll count me each one, right? So when I do it that way, and I multiply it, then I divide 0.0, oh, it gives me moles. It does not give, and this is giving me atmosphere, so I'd have to convert from this to moles. Let's do it the book's way.
I think now you use that from that formula for each. Because we got the total pressure now.
Yeah, we're just going at it different than they like it, right? So my
Oh, okay.
total pressure
Times in.
well, let's look at our mole fraction, right? So my mole fraction for each one, right? So is 0.0025 divided by 0.0038 equals 0.66, right? And let's do the next one. We get 0.001 divided by 0.0038, and that is 0.26, and then we go 0.003, not enough, 0.0003 divided by 0.0038, and that gives me 0.08. Okay, those add up, that's nice. Okay, and so those are my mole fractions. So if I multiply my mole fraction by my total, that should give me the partial pressure of each and every single one. So if I do 0.66 times 0.009613, I get 0.0063 atmospheres. Is that what you get?
Yeah.
Good. And that also matches what the book gets. And if I do 0.26 times 0.09613, then I get 0.025 atmospheres. Right, and I can do my last one. I go 0.08 times 0.096. Oh, I didn't do enough. 0.08 times 0.009613. I get a tiny number, right? 0.00077 atmospheres. So check out what you got.
Yeah.
Okay. Now your book takes a whole different approach to that, and I think it's going to be worth looking at both. Okay. So we'll do that real quick. I'm going to have to erase though to get at this because there's just not room. All right, so your book takes this approach. Pressure of H2, pressure of H2 is 2.50 times 10 to the negative third moles times 0.0821 liters, atmospheres, moles, degrees Kelvin, times temperature, which is 308 degrees Kelvin, And divide that by 10 liters. And that will also give me my 6.32 times 10 to the negative third atmospheres. Right? I can repeat that for each one, and then sum them up, and that'll give me my partial pressure. Okay? Probably easier than the way I took. But I tend to rush into things backwards. Let's try one more of these, okay? Erase this. Okay. 5.73 liter flask. 25 degrees centigrade. Contains 0.0388 moles of N2. Contains 0.147 moles of CO. Contains 0.0803 moles of H2. What is the total pressure in the flask in atmosphere? So find P total. Right, so to do that, I need to solve for each of these partial pressures and add them up. Right, so PV equals nRT. So PV equals nRT. I'm going to go pressure equals nRT over volume. Right, so we set this up. Number of moles is 0.0388 times R, 0.0821 times temperature is going to be, 298.13, right, degrees Kelvin, okay? Divided by my volume of 5.73 liters. And I'm going to repeat this for each one of these, right?
Yeah.
My last one here is 0.0803. Is that right? Yeah. Okay. She did get 1.137, 1.137.
Yeah.
Yeah. I cheated a little bit. I didn't feel like running this whole calculation every time, so I just did this times this divided by that, wrote it up there, and then just did that times that. That's a lot easier to me.
What I did was I added the rows and just did it one.
Yeah, it's easy too. Always a skin cat. All right. Oh, man. Let's do this last bit and then we will get out of here. My feet are tired and I want to quit right now. It's like, well, probably need to try to get through some content, so. I don't know why my feet hurt so bad today. You know, guys, they preach in like Jordans shoes and stuff like that. I can't do it. Like if I'm in a suit and all that, I gotta have on dress shoes. I can't be. I feel like a clown.
Yeah. It doesn't work well a suit with Jordan.
They do it, and I'm sure it helps their feet a lot better. I know the guys who preach in cowboy boots, but whenever I wear cowboy boots, they kill my feet. I don't wear them very often. They kill my feet.
That doesn't feel very comfortable.
All right, here we go. All right. A gas mixture used for anesthesia contains 2.83 moles of O2, 8.41 moles of nitrous oxide. The total pressure is 192 kilopascals, okay? So we want to know this. What are the mole fractions of each? Okay, and what are the partial pressures of each? Doesn't even seem very difficult at all. So add the two moles together and that would divide each one. That would give you a mole fraction, right? I get 11.24 moles total. You get that?
Yeah.
Okay, so my mole fractions are 0.252 for O2. Which means I should get 0.748 for N2O, right?
Yes.
Do they like those numbers? Good, 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 good. All I should have to do is multiply that by my total pressure, right, to get my partial pressure.
Yeah.
So 192 times 0.252 equals 48.384 kilopascals for oxygen.
Yeah.
And if I subtract 192, I should get 143.616 kilopascals for N2O.
Yep.
Okay, that felt like a waste. What is the pressure of a mixture? Do we want to do the next one? You want to do it or go home?
No, we can do
You
it.
want to do it?
Let's go.
All right, we're going to do it. Here we go. Last one of the day. What is the partial pressure, or what is the pressure of a mixture of 0.2 grams of H2 1.00 grams of N2. It's 0.200 grams, sorry. And 0.820 grams of arsenic in a container with a volume of 2 liters at 20 degrees centigrade. That's all it wants. Just wants to know the total pressure. Okay, so we just need to find the total number of moles, right?
Mm-hmm.
Okay, so 0.2 divided by 2 is 0.01, or 0.1, right? 1 gram divided by 14.02 grams per mole of nitrogen is 0.07 moles of N2. And then 0.820 divided by, I don't have the molecular or the formula mass of arsenic memorized, molecular weight of it. Is it?
It's 74.9.
Or no, that's not arsenic, it's argon. Sorry, which is going to be monatomic. So what is it?
39.94.
That's the molecular mass?
Yeah,
39 point what?
0.94. 95, this is 948, so.
Okay, so too late because I did 94, so I'm staying with it. So we have 0.02 moles of argon. Okay. Okay, so I add those up. 0.1 plus 0.07 plus 0.02, and I get 0.19 moles, right? So now I just need to plug that into my PV equals nRT. What am I solving for? I'm trying to solve for my pressure, right? So pressure equals nRT, my number of moles we said is 0.19 moles times 0.0821 times 293.15 degrees Kelvin divided by my volume, which we said was 2 liters. That's not bad at all. I didn't get the answer they got. Wait. What'd you get?
I got 2.3.
What's I got?
I think the number of number of moles of N2 is wrong.
Okay. Oh, it's by 28.2.
Yeah.
Ah, that'll change everything. Okay, so 1 divided by 28.2 is 0.035. Is that about right? Okay, well that'll change everything, won't it? Okay. Wow. Let's run that again. 0.1 plus 0.035 plus 0.02 is 0.155 moles. Okay, so let's rerun it. 0.155 times 0.821 times 293.15 by 2 is 1.865, which I think that's the right answer.
That's what I got too.
All right. Let's go home. It's time. Actually, it's time, so that's good. Oh, man.